So my English is like no Spanish English, more like Chilean English. So first of all, second, to thank the organizer for inviting me. First one, this title, Let's Get Rational, has nothing to do with some political statement. Even when I was finding this title, I was listening to the news. I was one of the presidents giving a speech. As I was told, I work more into Riemann surfaces, but today I want to talk a little about rational maps. So let me tell you a little about in the 80s, Sullivan was writing this series of papers, making a kind of dictionary between dynamics of rational maps and the theory of Kleinian groups. Like 3 first, and then was a 4th one. And the idea was try to find similitudes between these two theories, and essentially say, okay, there's a fact working for rational maps. It should be probably true for the dynamics of certain Kleinian groups. And in terms of Kleinian groups, there are ones very nice, which are those uniformizing closed Riemann surfaces. So Fuchsian groups called compact Fuchsian groups. So on that level, we have, for example, closed Riemann surface of genus G. We have associated this Teichmüller space of genus G, which is a complex manifold. And we have an action of the modular group, as I've seen before, in Teichmüller space. And we have as a quotient this orbifold, complex orbifold, which is the modular space. So I will try to give the talk in rational map and say something also a parallel. What is similar, what is not similar in that sense. So hope I'm successful in this. So first, let me introduce the actors of this picture. So these are the rational maps. So rational map, see, no, this is something else. What is the light? This, probably, yeah. So rational mass is just the quotient of two polynomials, which we assume to be roti prime. And we can collect all the coefficients of the polynomials in defining the rational map, and this provide us an injective map of the rational space, the space of rational map of degree D into the projective space. And this image is just the complement of a hypersurface, which is the resultant of two polynomials. So in that sense, we see that the rational space of has a complex manifold structure of the dimension 2D plus 1. And in this space, also we have an action by conjugation by Möbius transformation. We can take a rational map, take a Möbius transformation, and just conjugate, and you get a new rational map. And that action is holomorphic in that complex structure. The quotient of this rational space, and by the Möbius transformation, it was called the modular space of rational map of degree D. So this is a complex orbifold. I will go back to this. And of course, degree 0 and degree 1, we know them. So we are going to stay from now on degree at least 2. So I was telling, Milnor already observed that in this paper, the 93, that the modular space of rational map carries a structure of a complex orbifold, so has singularities, and the dimension is 2 times d minus 1. And moreover, for degree 2, there is a explicit model, which is the complex C2. Essentially, this how he does is just, take a rational map of degree 2, then you have 3 fixed points, counting multiplicity. At each one, you have the multiplier, which is the derivative of the fixed point. Since we don't care which is the first, second, or third point, we take the symmetric functions, the 3 symmetric functions on the 3 multipliers. One can realize that one of these symmetric functions can be obtained from other 2. Using these 2, you get the map from N2 to C2. And in fact, one can, taking these two rational symmetric forms, one can reconstruct the rational map up to conjugacy. Yeah, at least for me, I don't know an explicit model of the model space for degree at least 3. What is known, for example, that if one tried to emulate Milnor's idea to take the multipliers of fixed points, or go to take the multipliers of the periodic points of period 2, period 3, and the set of period, one can construct also a map to some, from the model space MD into the some power of C, but this happened by Macmillan observed that this is for take periods sufficiently large, then this will be finite to 1, but will be at the lattice maps will be constant, so it's not a good thing. So still, no. I must say here that Joseph Silverman also have done the situation, but for any field and any characteristic. Okay. So, I have said we are looking at this action of the Möbius group as a group of holomorphic automorphism of the rational space, and the stabilizer of a rational map is what we call the group of holomorphic automorphisms of the rational map. This group is finite, and the reason is because a Möbius transformation is uniquely determined by the action at 3 different points. So one can do is just take for the phi periodic points of certain period, so it will be a finite number, and the Möbius group, the stabilizers will move this space, this set of finite set into itself. So in that way you can check that the group of automorphic or holomorphic automorphism is finite. In general, it's trivial. Okay, so what we know also, we know that the finite group of Möbius transformations are the trivial one, cyclic groups, the ideal groups are the Platonic one. So here I put the A4, alternative 4, alternative 5, and the symmetric group as 4. And recently, Miasnikov, Stott, and Williams in recent paper has shown that for each of these groups that you choose, you can find a rational map of certain degree for which the group is the full group of holomorphic automorphism. Okay, and moreover, they say, okay, if you want to have A4, then there is a relation for the degree. It's not for any degree, of course. I want to just recall the result for the cyclic case in this now. So essentially, they say, yeah. So let's take integers d and n bigger than 2. This will be the degree of the rational maps, and will be the order of the automorphisms I'm looking for. And then, so there is a rational map of degree d and meeting holomorphic automorphism order n, if only if then there is a relation between the degree and n. In this case, the degree has to be congruent to -101 modulo n, right? Also, if you have one of these rational map, you can find a normal form. That the reason is because you have any cyclic group of order n of Möbius transformation, you can conjugate it by a Möbius transformation, so that is just rotation. Yeah, so this I didn't put C go to square root of n root of unity times z. So, and under this you can write the rational map in this normal form. Just C times a rational map in theta to the n, and of course you need some conditions in order to keep the degree. If not, you can go down degrees. So you have the normal forms of these rational maps having a cyclic group of holomorphic automorphism. They also do it for each of the possibility, for the ideal group, for alternative groups, okay, and the symmetric group. So, and here you see there are 3 conditions. Essentially, they are mutually disjoint, except for the case n equal to, where you, of course, you have equivalence in here. Yeah, no, this one and this one. But For example, if you have a degree 2 rational map and you want to look which automorphism, holomorphic automorphism it may have, then the result tells us, okay, they only happen for involutions or order 3 automorphisms. They will be back later for this. So let's come back. So we have defined the space of rational map, which is kind of the Tejimines space, not correctly, but kind of this. We have the model space of rational map, equivalent that we have the model space of Riemann surfaces. And we have now the grouping here. In there was the group of Möbius transformations, and here is the modular group. Okay? And also there are some stratification and study of the group, final group of holomorphic automorphisms of Riemann surfaces, and it has to do related with the so-called the branch points, the branch locus of modular space. I will come back. So from this form of this rational map emitting this holomorphic automorphism, one can find that in modular space, the classes of rational map admitting a cyclic group of order n as a subgroup of holomorphic automorphism will be connected, and the dimension will be the corresponding, in each case, depending on the congruence situation. But observe that the case n equal 2 happens in each degree, equal to 2, and this is exactly when they have the maximum dimension stratum. Okay? Yeah. This will be a main point later. So let me talk about the branch locus. So I told you here, in the model space of Riemann surface, the branch locus correspond to the class of Riemann surface admitting automorphism, not trivial automorphism. For I will take G bigger or equal than 3. If I put G equal 2, because everything is a hyperelliptic, I have to tell about the reduced group of holomorphic automorphism. But anyway, there is a locus of Riemann surfaces admitting many automorphisms. And in rational map, we have the same. We have the locus of rational maps which admit holomorphic automorphism. So it is known that for degree only 3, similar to what happened in the case of model space, for genus bigger than 4, and here for degree bigger or equal than 3, that this branch locus is exactly the locus of point where this orifice, the model space, fails to be topological manifold. Yeah. Yes. So for d equal 2, this is not true, and I will show you what is going on. So in degree 2, Fujimura, in 97, observed that using Milnow's model, C2, yeah, the locus of rational map, classes of rational map degree 2 that admit holomorphic automorphic, not trivial ones, is given by this locus, this cubic one. And remember that I told you before that in degree 2, there were 2 types of automorphic, degree order 2, order 3. And in here, happened that in this, you have a cusp, which is this. This is the case where you have both type of automorphisms, one of order 2, one order 3, and they generate the dihedral group, D3. And the rest of the cubic separations is exactly those admitting C2, actually. So one can see that in degree 2, modular space, well, we already saw it's just C2, no singular part, but the branch locus is a cubic, particularly something connected. And one of the questions, so here I also have the branch locus. And in series of papers by Milagro Izquierdo, Bartolini, Antonio Costa, they have shown that in model space, the corresponding branch locus usually is disconnected. And there are some finite number of genus where it is connected. But what is going on for the rational map? We observed that doesn't matter in which degree we are, the branch locus is always connected. So there we see a main difference, what is going on with rational maps and what is going on with closed Riemann surface stuff. Yeah? Okay. So let me talk now about anti-holomorphic automorphism. So what I'm going, in here in module space also as a complex orbifold, there is a natural complex structure, real structure, which essentially just you take a Riemann surface, you have the conjugate Riemann surface structure that produces an involution, anti-holomorphic involution here, whose locus of fixed point are the real point of that real structure. So we can ask for the same for the module space of rational maps. So I talk about extended Möbius transformation, and just the composition and Möbius transformation with usual complex conjugation. See, these are the anti-holomorphic automorphism of the Riemann sphere. And I want to mention now only two of them for the moment, involutions. So I have an extended Möbius transformation which has order 2. There are in two flavors. Either it's a reflection, so it has fixed point. The fixed point is a circle in the Riemann sphere, or it is an imaginary reflection which has no fixed points at all in the Riemann sphere. So they are conjugated, this last one, to reflection unit circle rotated by 180 degrees. So again, each extended Möbius transformation conjugate rational maps to rational maps, and we can take those which leave invariant the rational map, and that will be the anti-holomorphic automorphism of the corresponding rational map. In general, it may not have anti-holomorphic automorphism. Sometimes it does. So what is the relation? Remember that we had a map with we put the rational space, we embed it into the projective space by just collecting the coefficients. The conjugation by conjugation is nothing else than just conjugation of the coefficients of the polynomials involved. So it's just usual conjugation at the level of the projective space. Such involution, anti-conformal involution, descends to the module space as an anti-holomorphic automorphism for the 2. The fixed point is fixed point, which I call MDR, is the locus of real point of such a real structure. So it's something in here. But now I'm looking. So something in here. For the Riemann surface also, and for the module space. The real locus means probably I will come back in here. It's important to mention this. So what is the real point? The fixed point of this involution. But this is equivalent to those rational maps admitting anti-holomorphic automorphism. So they are conjugated, are equivalent by PSL2C to their conjugated. So if you want to look the real point, you just look if it admits or not an anti-holomorphic automorphism. So if such an automorphism turns to be a reflection, so this reflection has a circle of fixed points, we may assume after conjugation that is the real line union infinity. So this rational map must keep invariant this real line, the standard real line, and then it means that this rational map will be defined as a rational map with coefficients in R. So I call this MDR in the parentheses, not to confuse with MDR in the top. And this is connected and is of dimension 2d-1 real. So in the case of, here I will put the modular space of rational map aside with this modular space. So we have at least one component in here, one connected component, which are the real rational map. Here is sometimes complicated when talk about the real rational map in the sense of the real point of the attraction and real rational map as those which are definable over the real. So yes, one has to be careful with this. So what happened with the rest of them? So the rest of real points of this real structure are the so-called these pseudo-real rational maps. So what is our pseudo-real rational map? Are those rational maps admitting anticonformal automorphism, but none of them being a reflection. Okay? But it may have imaginary reflection as automorphism. So if someone know about this in Riemann surface, know that in that equivalency, it's real if admit anti-holomorphic involutions. It may or not have fixed point. So it may different. So Silverman, in the 95, he observed that for even degree, there are no pseudo-rational maps. And in odd degree, there are always pseudo-rational maps by showing a particular examples of pseudo-rational map. His examples are rational maps admitting no holomorphic automorphism and one imaginary reflection as an automorphism. So, let's try to look at this pseudo-real rational map. So first, we are going to look, after conjugation by image transformation, we may assume that such anticonformal automorphism over the N is this one. We can conjugate to this reflection of the unit circle by some rotation. Yeah. So we are going to, in the rational space, we have the locus of this rational map admitting such an automorphism, anti-holomorphic automorphism, and its projection will be in the modular space, the corresponding one. So we want to know what these objects are. So how to put in here, how this will look in here, and which relation are we already parting you have here. So, of course, there is an stratification. So if you have an anti-holomorphic automorphic order 2n, then you write n in this way, then you have that those having automorphic order 2n, we have this automorphic order 2 to the s plus 1. So we only have to worry with this big strata. And also, for example, if any so, then you see that the one that has anti-holomorphic involutions means imaginary reflections and no automorphism at all. And these objects, they only intersect at the real ones. Okay? So we have real ones. So you can think of how it's called spina dorsal and the paletas. I don't know. This is like, it will look like the configuration. Yeah. So with Saul Quispe, we were trying to say, okay, if I want to look a rational map with an imaginary reflection as an automorphism, how much looks like. So it's the normal form. So one can just, as we know, only D must be odd, and if, in fact, if D is odd, then this will have the rational map admit an imaginary reflection, if only it can be written in this form, where there is some relation between the coefficients. So you see the coefficients in the top can be any complex number at priori. And in down, then there is a relation of this form. They appear the conjugated of the ones here, but looking in the other direction, and some multiplied by some rotation. Okay, but in this, all of them, some of them may have even reflections, for example, or something like that. So this is just the configuration, and this form permits to see that in the rational space, in the modular space of those rational map admitting imaginary reflections are connected and has corresponding dimensions. Okay, so important they are connected. But the problem is if I take out the real ones, well, if there are real ones are here. So already disconnected part. So essentially, if we add in here the ones admitting, the pseudo-reals admitting imaginary reflections, it's still connected. It's still connected. But now it may happen that there are, well, also there for the situation. So important here, I should mention before, okay, this is what I just said, so I will not say any longer. So now it may be pseudo-rational maps admitting no imaging reflection. So it may have anti-holomorphic, automorphic order 4, and so on. So we have to take care of that. Again, if we want to look at this rational map admitting anti-holomorphic, automorphic order 2n, with n at least 2, we know that the degree has to be at least 3 odd. Also, there is a relation between d and n, either n divided n minus 1 or n divided d plus 1, but the correct one, which divide, must be even. So there are some constraints for this. Not both of them are even. And in any of the choices, so you take R, the one that corresponds to be even, in the case that it is possible. Then the rational maps admitting this automorphism or the 2n anti-holomorphism must be conjugated to one of these forms, where C is again a rational map where you can find the form of the coefficient, just by directly putting down the automorphism. Yeah? So, for example, in degree 3. In degree 3, the previous results say that if you look at which anti-holomorphic automorphism of the 2n may appear, so it say only happen order 4. Anti-holomorphic, automorphic. And these rational maps must be of this form. But then you can take out A and A bar in here, so you put in here, again, it's a absolute value 1 number, so they look like this. And these one are exactly this one-dimensional locus of rational map of degree 3 admitting anti-holomorphic automorphism order 4 and no more. There's no more, just to mention. So, as a corollary of this normal form is that you can say that, okay, the space of rational maps in the rational space admitting anti-holomorphic automorphic order 2n is connected, and it's equivalent to a precise form because of the normal form of the rational map. And the projection, again, will be connected and the corresponding dimension, one less. Yeah, so the same happened for the other case because we have two cases. D minus 1 divided by n is even, or D plus 1 divided by n is even. So in each case, there is a form, a presentation, and the corresponding dimensions. So, more to say. Essentially, with this, already one can show that all the real locus in here is connected. What happened in the space of the real locus of model space? It has been proved again that is connected. So here we have a result that is similar for the component of the real part. So what about automorphism of pseudo-real rational maps? So if you have a pseudo-real rational map, it's group of holomorphic automorphisms, either trivial or cyclic. So it cannot appear as the other type of group. Also in any odd degree, you can have anti-holomorphic rational map with anti-holomorphic automorphic order 4. But for example, in 3 and 5, for example, there is no rational map admitting anti-holomorphic automorphism order A. So the 4 is the one that essentially keep in every degree, but if you want to look for another orders, it may happen that in some degree you can find an example, in other degree you cannot find an example. But degree 4 is okay. This is also, this point in here, this also was an ingredient in the connectivity property of here. So, Zimmerman observed the following. If you have a pseudo-rational map whose holomorphic group of automorphic trivial, this is equivalent for it to have an imaginary reflection as an anti-holomorphic automorphism, almost by the definition. Also, you can describe them by this property. I will not go with this. What about a pseudo-rational map with cyclic group of holomorphic automorphic, not trivial? So in that case, one can again say, well, if you want to look for the rational map which must have the of degree, with a group of holomorphic automorphic to be a cyclic group of order at least 2. Then the rational map has to be essentially of this form with some constraints in here on this coefficient of the rational map C involved. So with this you can construct explicit pseudo-rational maps admitting this. So the previous known example, explicit example, were Silverman example with trivial group of holomorphic automorphs. So this provides a lot of more examples of the rational maps with holomorphs. For example, if you just plug in here, put any complex number, choose any for rotation, and just the relation before, it just can read in these ones, and then you use this rational map with these constraints, then the rational map, which is set times C to zeta to the n, will be a rational map with anti-holomorphic automorphisms of order 2n, and this will be pseudo-real. Yeah? For example, you just put NC and all these numbers, then C turns to be this, the rational map turns to this degree 12 one, and this one is a rational map of degree 13, whose group of holomorphic automorphisms is the cyclic group of order 6, and the anticonformal automorphism is generate the C12 group. So you can construct explicit ones if you like. What about a Silverman example? So these were pseudo-rational map without holomorphic automorphism. How you construct all of them? So essentially you do the following. You just take a rational map so that they satisfy certain constraints. That's not difficult to check of them. And then this rational map observed here is not a mistake. The n is already upside. Okay? So the idea is just to take pseudo-rational maps with a cyclic group and then try to project by the cyclic group and to construct new pseudo-rational map without automorphism. So this is possible, and then you get pseudo-rational map with trivial group of holomorphic automorphs. So you can classify all these pseudo-rational maps in terms of holomorphic automorphism. So I told you this should have been before. For these three, the pseudo-rational map, the local pseudo-rational map is disconnected, but when you plug together with the locus of real rational map, this is connected. Yeah? So we have this. So for the branch locus, which is concerned with holomorphic automorphism, is disconnected. It's connected, and for the real ones, is connected. At the level of model space or Riemann surface, the locus of the branch locus means those Riemann surfaces with many holomorphic automorphism is disconnected in general, and the one with the real locus is connected. So in some cases coincide type of result, another case get different. So let me go to another part of this relation between Riemann surfaces and rational map. So we know that by Riemann rock that each time that you have a closed Riemann surface, you can describe it by complex algebraic curves. So when you have complex algebraic curves, you have polynomials in there defining this curve. So you can take the group of automorphism as a field. I put in here the gal C. And then you can apply this to these algebraic curves, and you can you make action of the Galois group in the world of Riemann surfaces and move point in the modular space. We can do the same at the level of rational map, since rational map are just defined by polynomials. So here we have, each time that we have a rational map and we have an element in the Galois, just sigma is to apply sigma to the coefficients of the rational map. We get a new rational map with the same degree, many results. But it may happen that the complex structure, the dynamics of the rational field could be different at the dynamic of this new rational map. So, okay, So, if we look all this, we collect all this sigma so that this action keep in the same class, conjugacy classes, then this is called the field of moduli. And it happens that this field of moduli, let me see, I put it here, it was proved by Koizumi that coincide with intersection of all field of definition. What is the field of definition of rational map? Just take a rational map. You can conjugate by Möbius transformations. You have a lot of conjugated, and each time that you have one of them, you have the coefficient, and you look at any field that contains this coefficient, that will be a field of definition. So, in this case, this field of moduli will be like the smallest possible field of definition if it is a field of definition. So, in the case of pseudo real rational maps, what is going on? The fact that we have anti-holomorphic automorphism, this is enough to see that the field of moduli has to be a field of the reals. And if the rational map admits a reflection as an automorphism, then the real map will be definable over R, as we observed before. So to look if examples of rational map which are not definable over the field of moduli, well, just construct any pseudo-real rational map. That will be, we cannot be defined over R because we don't have reflections, but since there are admit anti-holomorphic automorphic, the field of moduli will be R. So, a result by Silverman said that if we have a rational map of even degree, or it is conjugated to a polynomial, then the field of moduli is a field of definition. And essentially, the proof of that is applying essentially Bales-Desens-Galois theorem and using the fact that, for example, if this event we have an odd number of fixed points or so on, so we have odd degree divisors which are rational over the field of moduli, we can apply results. This is the idea. And for the odd degree, already we have this pseudo-rational. So for odd degree, this result is not true. So I was wondering, for example, some time ago, if how far I can find a field of definition of a rational map of odd degree over the field of moduli. And it has been conjectured for the case of Riemann surface. For Riemann surfaces, also when we look at it as a complex algebraic curve, again it's the same. If the field of moduli of the rational of a real Riemann surface is again the intersection of all the field of definition, and it is known that always there is a field of definition which is a finite extension of the field of moduli. It has been conjectured that when the Riemann surface cannot be defined over this field of moduli, can be defined on an extension of degree 2. And this happens to be true when the surface has no automorphism, because it can be defined over the field of moduli by Weil theorem. Jugen-Wolfart proved that if the surface is quasi-platonic, means if the quotient of the surface by its group of holomorphic automorphic at the sphere branch at a 3-point, again, the surface can be defined over its field of moduli. And if the surface quotient by the group of holomorphic automorphism is the sphere, then can be proved that the surface can be defined over other. It's field of moduli of a quadratic extension, but in general it does not. This can be false, this conjecture, or not. What happened for the rational map? For rational map, it's much simpler to work. And it happened that it's true. It means if a rational map of odd degree can be defined over its field of moduli, certainly can be defined over a quadratic extension. Here is a problem now. A more practical one is, okay, even if you have your rational map, which can be defined either of its field of moduli or a quadratic extension, find a rational model of this rational map over that minimal field of definition. This is something which computationally sometimes is difficult for high degree. So, just finishing, one of the questions we were asking if, okay, all these examples known examples of rational map which could not be defined over its Phylum moduli were pseudo-rational map. And I have told you before, the main reason because it's simple. Just find a rational map admitting anti-holomorphic automorphism, but no reflection. So kind of simple to find. That is the example. So we're wondering, what about this rational map we can be defined over the reals? Could be an example in that world. And the answer is yes. So, for example, this rational map of degree D, the odd, which are defined over a quadratic extension of Q, real quadratic one, has a Phylum moduli Q. And this cannot, and we show that this cannot be defined over Q. And this is, has nothing to do with holomorphic, anti-holomorphic automorphism in this case. So in real here is, the main role is that here the coefficient we are showing in here is element in here in this quadratic extension norm 1. So you can choose any one. And essentially playing with this is nothing difficult. But we were expecting the opposite. We were hoping that every real rational map could have been defined over the Phylum moduli. But this is an example, and so many examples can be done. So to finish, something else before. So for Riemann surfaces, the following result is known by Gareth Jones, I suppose, Silverman, Manfred Streit, and Wolfram probably also, that take your favorite Riemann surface, closed Riemann surface. Assume that this is real. That means it can be defined by an algebra variety over R. On the other hand, you have another model of this Riemann surface by another algebraic curve defined over Q bar. Then you can find always a new model which is defined over the real algebraic numbers. So the question was, is true at the level of rational map? Should be. And the answer is yes. So if you have a rational map which is defined, which is real, so can be defined by a model over the reals, and it can be defined also by another model over Q bar, then you can find a third model over Q bar inter R. So it's the same happens. So again, the world of Riemann surfaces and rational map has a lot of coincidence and only one deception, so it's winning the coincidence than from this. And finally, just to say you that on November of this year, in Chile, in south part of Chile, where this nice volcan is there, will be a Congress on Riemann surfaces, and everyone is invited to go over there. We are happy if you go over there. You can even claim here. Yeah. So thank you very much.